Good morning, everyone. Today we are going to see the topic light energy. The key concepts which are covered here are spherical mirrors, concave and convex mirrors, terms related to spherical mirrors, ray diagrams, rules regarding the formation of images by spherical mirrors, images formed by concave mirrors, images formed by convex mirrors, uses of concave and convex mirrors. Refraction, terms related to refraction, laws of refraction, rules of refraction, refraction through glass slab, refraction through prism, dispersion of white light, formation of rainbow. Light energy. Light energy is essential to see the wonderful and colorful world around us. It causes a sensation of vision and helps us to view the objects. Light causes many optical phenomena such as image formation by mirrors, twinkling of stars due to refraction, formation of rainbow due to dispersion of white light. Spherical mirrors. Mirrors need not always be plane. Even a curved surface can also act as a mirror. For example, if you hold a stainless steel spoon and bring one of its face close to yourself, you will see a distorted image. If the face of the spoon which curves inwards is brought closer, you will see an inverted image. On the other hand, if you bring the other face of the spoon which bulges outwards, you will see an erect image. A mirror in which refracting surface is curved is called a curved mirror. The most common type of curved mirrors have spherical shapes. Such mirrors are called spherical mirrors. A spherical mirror is a part of hollow sphere with one of its curved surface polished in silver while the other acts as a reflecting surface. A spherical mirror whose inner surface curving inwards is reflecting the surface and the outer surface bulging outwards is polished is called concave mirror. A spherical mirror whose outer surface is reflecting surface and inner surface is polished is called a convex mirror. Let's see the terms related to spherical mirrors. Pole. Geometrical center of the spherical mirror denoted by P. Center of curvature. Geometrical center of hollow sphere which is denoted by C from which the mirror is formed. Principal axis. Straight line passing the pole and center of curvature denoted by Px. Radius of curvature. Radius of the hollow sphere of which spherical mirror is a part denoted by small letter r. Principal focus or focal point. The point on the principal axis where all the rays of light parallel to the principal axis meet or appear to meet after reflection is called the principal focus or the focal point. In case of concave mirrors, all the rays of light parallel to the principal focus are converging mirrors. In convex mirrors, the rays of light parallel to the principal axis diverge after reflection and appear to come from the principal focus, which are called diverging mirrors. Focal point. The distance between the pole and the principal focus is denoted by f, which is called the focal point. F is equals to r by 2 implies r is equals to 2f. Aperture. The area of mirror from which reflection takes place is called its aperture. It basically denotes the size of the mirror. Linear aperture. The length of the straight line joining two opposite extreme points on the periphery of a spherical mirror is called its linear aperture, denoted by the straight line mm. Angular aperture. Angle subtended by the two opposite extreme points on the periphery at the center of curvature and is denoted by angle MCM. Real and virtual images. You know by now that we must have a reflecting surface to form the image of an object. For the formation of the image of an object, the corresponding reflected rays should either actually meet or appear to meet at a point. This point is known as the point of image formation. Image formed due to actual meeting of reflected rays at a point is called a real image. On the other hand, the image formed when reflected rays only appear to meet at a point but don't actually meet is called the virtual image. The table shows the differences between the real and actual image. A real image is formed by actual meeting of the reflected rays, while virtual image is formed when the reflected rays appear to come from a point but do not actually meet. A real image can be obtained on a screen. A virtual image cannot be obtained on a screen. A real image is always inverted. A virtual image is always erect. A real image is formed on the same side of the mirror as the object. A virtual image is always formed behind the mirror. Ray diagrams. You know that the image formed by a plane mirror is erect, virtual, and is of same size as that of object, but the nature and size of images formed by spherical mirrors depend on the nature of the mirror, distance of the object from the pole of the mirror, and focal length of the mirror. The exact nature and size of images formed by objects kept at different positions in front of the spherical mirror can be determined by tracing the path of light by drawing simple diagrams. Such diagrams are called the ray diagrams. Object is represented by vertical arrow and is kept perpendicular to the principal axis in a ray diagram. Construction of images using ray diagrams. For convenience, any two of the following rays can be taken as incident rays for locating the image. An incident ray passing through the center of curvature of concave mirror reflects back along the same path without any deviation. In case of convex mirror, an incident ray which appears to move towards the center of curvature is reflected back along the same path without any deviation. An incident ray in case of concave mirror is parallel to the principal axis and passes through its focus after reflection. In case of convex mirrors, the incident ray after reflection appears to come from the focus of the mirror. Did you know that Cloud Gate is a 110-ton highly polished convex stainless steel centerpiece sculpture in Chicago that is beautifully distorts the reflection of the city and the skyline? Inspired by liquid mercury, the sculpture is among the largest of its kind in the world, measuring 66 feet long by 33 feet high. It is designed by famous British artist of Indian origin Anish Kapoor. An incident ray passing through the focus. In a concave mirror, an incident ray passing through the focus is reflected parallel to the principal axis. In case of convex mirror, the incident ray which appears to move in the direction of the focus of the mirror is reflected parallel to the principal axis. A ray of light incident at the pole of the mirror. In a concave mirror, a ray of light incident at the pole gets reflected along the path such that angle of incidence is equal to the angle of reflection. This is also true for convex mirror. Images formed by a concave mirror. The image formation by a concave mirror and the ray diagram for different positions of object AB are explained below. When the object is at infinity. When an object is at infinity or very far away, the rays coming from it are considered to be parallel to each other. Consider two parallel rays coming from a distant source. one striking the mirror at its pole and other passing through its center of curvature. The ray incident at the pole affects at the same angle, obeying the first law of reflection. The other ray will retrace its path after reflection. The two reflected rays intersect each other below the principal focus. So the image AB is formed at the focus and is real, inverted, and highly diminished. When the object is beyond the center of curvature, let us consider two rays, one parallel to the principal axis and other passing through the principal focus. The ray parallel to the principal axis passes through the focus of the mirror after reflection. The incident ray passing through the principal focus of the mirror is reflected parallel to the principal axis. The two reflected rays meet at a point between F and C. The image AB is formed between F and C and is real, inverted, and diminished. When the object is placed at the center of curvature, let us consider two rays, one parallel to the principal axis and other passing through the focus. The ray parallel to the principal axis passes through the focus after reflection, and incident ray passing through the principal focus is reflected parallel to the principal axis. The two reflected rays meet at C, so the image AB is formed at C and is real, inverted, and of the same size as that of the object. When the object is placed between C and F, let us consider a ray of light coming from the object parallel to the principal axis, while another one passing through the focus. In such a case, the image AB is formed beyond C and is real, inverted, and enlarged. When the object is placed at the focus, let us consider an incident ray parallel to the principal axis of the mirror and another passing through the center of curvature. The two reflected rays go parallel to each other and meet at infinity. Since the reflected rays meet at infinity, the image is real, inverted, and highly enlarged. When the object is placed between P and F, let us consider an incident ray parallel to the principal axis of the mirror and another passing through the center of curvature. In this case, the two reflected rays do not meet in the front of the mirror. They appear to meet beyond the mirror when extended backwards. Thus, the image AB formed is virtual, erect, and enlarged. In the following slide, we are seeing the images formed by a concave mirror in a tabular form. Images formed by a convex mirror. Let an object A be placed in front of the convex mirror. An incident ray that is parallel to the principal axis appears to be reflected back from the principal focus of the mirror. Another incident ray that appears to pass through the center of curvature of the mirror retraces its path after reflection without any deviation. The two reflected rays appear to meet behind the mirror when extended backwards. The image AB by convex mirror is always virtual, erect, diminished, and formed between F and P, irrespective of the position of the object with respect to the mirror. The next subheading is uses of spherical mirrors. In that, we are going to find the uses of concave mirrors. Concave mirrors find a large number of uses in our daily life. Some of them are listed below. Concave mirrors are used in solar heaters to concentrate sun rays towards the food in the container to be heated. They are used as reflectors in headlights of automobiles, in searchlights, in floodlights, and in torches. When the bulb is placed between the focus and pole, as in floodlight, a divergent beam of light is obtained that can spread over a large area. But if the bulb is placed at the focus of a concave reflector, as in case of torch and the headlights of a car, a powerful beam of parallel light is obtained. They are used by dentists to see an enlarged image of a tooth and other areas in the mouth. Concave mirrors are used by doctors to focus light and magnify images of small internal body parts such as inside of a ear and nose. They are used as a shaving mirrors. Concave mirrors are also used in reflector type telescopes. Did you know that a Dutch scientist named Christian Huygens, also a mathematician, studied spherical lenses? He published the mathematical theory of optics that forms the basis of modern optics today. He also studied the transit of planets Mercury over the Sun using a telescope. Uses of convex mirrors. Convex mirrors are used as street light reflectors since they can diverge rays over a large area. As convex mirrors always form an erect and diminished image, therefore they are used as a rear view mirrors in vehicles to get wider view of vehicles coming behind. They are used as vigilance mirrors in departmental stores, malls, and offices. Refraction of light. Place a pencil in glass of water and immerse a coin in a glass of water. What do you notice? The pencil appears to be bent at the point it enters the water, and coin appears to be raised. This optical effect occurs due to bending of light. When light travels from one transparent medium to another transparent medium of different density, it bends from its original path at a surface of separation of two media. This phenomena of bending of light is called refraction. How refraction occurs? Refraction occurs because light travels through different media at different speeds. Light travels the fastest in vacuum at a speed of 3 into 10 to the power of 8 m by s. The speed of light in air is also assigned the same value for the practical purpose. The speed of light in some other common transparent medium is given in the table below. The media in which light travels faster are called optically rarer media, and those in which light travels slower are called optically denser media. For example, between air and water, air is optically rarer and water is optically denser. Whereas between water and glass, water is optically rarer and glass is optically denser. When light enters an optically denser medium, its speed becomes slower. To compensate for the change in the speed, light readjusts its path to choose a shorter route out of the denser medium. The reverse occurs for light entering optically rarer medium. Terms related to refraction. To understand refraction better, we need to learn some terms related to it. Let xy be the boundary of separation of two media, air and water. The ray of light AO falling on xy is called incident ray. The point O at which the incident ray enters the second medium is called point of incidence. The incident ray bends at the point of incidence. The ray OB represents the path of light after bending at the surface of separation. This is called refracted ray. An image line NM drawn perpendicular to the surface of refraction at the point of incidence is called the normal. The angle AON between incident ray and the normal is called angle of incidence. It is generally represented by small I and is known as angle I. The angle BOM between the refracted ray and normal is called angle of refraction and is represented by angle small r. Effects of refraction of light. Our atmosphere also refracts light. It is made up of different layers. When light from any source passes through the layers of our atmosphere, it undergoes refraction many times. For example, stars appear to twinkle due to refraction of light coming from them. Refraction of light causes mirages to be observed in a hot sandy desert. The refraction of sunlight causes advanced sunrise and delayed sunset. Laws of refraction. Refraction of light is governed by two basic laws. These are the incident ray, the normal at the point of incidence, and the refracted ray all lie on the same plane. For a given pair of media of different densities, the ratio of sine of angle of incidence to the sine of angle of refraction is always a constant. That is, sine I by sine R is equals to constant. This law was first stated by Dutch astronomer Willebroord Cornelius and is therefore known as Snell's law. The value of constant is fixed for a set of two transparent media and depends upon their nature. It is called refractive index of the second medium with respect to the first and is represented by Greek letter mu. Refractive index is a ratio of two similar quantities and thus has no units. Refractive index of a medium with respect to vacuum is also defined as the ratio of speed of light in vacuum to the speed of light in the given medium. Mu is equals to speed of light in vacuum by speed of light in medium. The table shows the refractive index of some materials with respect to vacuum. Air 1.003, water 1.33, alcohol 1.36, diamond 2.42, kerosene 2.44. Let's see the example of rules of refractive index of a medium. The speed of light in vacuum is 3 into 10 to the power of 8 meters per second, and in water it is 2.25 into 10 to the power of 8 meters per second. Find the refractive index of water with respect to vacuum. Solution would be refractive index of water with respect to vacuum is speed of light in vacuum by speed of light in water, which is 3 into 10 to the power of 8 meters per second by 2.25 into 10 to the power of 8 meters per second, which is equals to 1.33. So when we say that refractive index of water is 1.33, it means that light travels 1.33 times faster in vacuum than in water. Rules of refraction. A ray of light traveling obliquely from a rarer medium to denser medium, for example, from air to water, bends towards the normal at surface of separation of two media. In such cases, the angle of refraction is less than angle of incidence. A ray of light traveling obliquely from a denser medium to a rarer medium bends away from the normal at the surface of separation of two media. In such cases, the angle of refraction is more than angle of incidence. When a ray of light strikes the surface of separation of the two media at the right angle, that is, incident ray strikes the surface normally. It travels along the same straight line path without any deviation. If the path of light is reversed, it retraces its path. Refraction of light through a parallel-sided glass slab. A glass slab is a small cuboid made of glass and is generally used to study refraction of light. The path of a ray of light can easily be traced as it gets refracted through a glass slab. Refraction of light through a prism. A prism is a glass block that has a triangular cross-section formed by three rectangular faces. The rectangular faces are the refracting surfaces, and the angle made by any two adjacent surfaces is called the angle of the prism. In the figure, xy is the incident ray, xy is the refracted ray, zr is the emergent ray, angle I is the angle of incidence, Angle R1 is the angle of refraction at the first phase. Angle R2 is the angle of incidence at the second phase. Angle E is the angle of emergence. Angle D is the angle of deviation. Angle A is the angle of prism. N1 is normal at point Y. N2, N3 is normal at point Z. Dispersion of white light by a prism. You have seen that prism deviates a ray of light incident to it. The phenomena of splitting of white light into its constituent colors is called dispersion. It was first studied by Sir Isaac Newton in 1666. He found that white light consists of 7 colors and it splits into 7 components when allowed to pass through a prism. The band of 7 component colors of white light can be obtained on screen in a fixed order. The order of 7 colors is violet, indigo, blue, green, yellow, orange, and red, which is called as VIBGR. This band is the 7 colors is called spectrum. Why does dispersion occur? Dispersion of light occurs because the refractive index of a medium with respect to another medium is different for different colors. Red color deviates or bends the least, whereas violet deviates the most. This is why red forms the top band and spectrum and violet forms the bottom band. If two prisms are placed next to each other such that their adjacent faces are parallel to each other and a ray of white light is allowed to fall on refracting surface of one of them, then the first prism on which ray of light falls will disperse the light into 7 colors. When this dispersed light enters the second prism, all the 7 components of light reunite and a ray of white light emerges out from the prism. Therefore, two prisms kept opposite to each other behave like a glass slab. Rainbow. The most fascinating example of dispersion in nature is the rainbow. It is visible in the sky after a spell of rain and is formed due to the dispersion of sunlight. Just after a rainfall, there are a large number of water droplets suspended in the atmosphere. These droplets act like tiny prisms. When sunlight passes through these spherical droplets, it undergoes dispersion. With a large number of water droplets contributing to this phenomena, we get to see a huge continuous band of 7 colors displaced in the sky.